Okay, example. Let's do our case of 2 coins in which our sample space is equal to H, H, HT, TH, TT. And we want to then, the first thing is we want to partition this into 2 sets. Now, usually that partition is dependent on the problem that will make it simple. So there's 2 in the text. It gives the partition, says, well, you could partition it with just each element being a single set, right? So because the sample space is just the union of all the simple events. But let's choose a little bit less less numerous one. Well, we have event 1 equal to the set that has at least one H, and E2 equals to TT. Okay, well, the law of total probability says, let's say we have, and we want to know what the probability of, let's say we wanted to know the probability that TT would occur. You'd have 2 tails. Well, I mean, this is trivial because you know the answer is 1/4. But the idea here is to use this to understand. So the law of total probability for this case would be, well, this is the probability that TT occurs given that event 1 occurs times the probability that event 1 occurs plus the probability that 2 tails occur given that event 2 occurs times the probability of event 2. Okay, well, we can see that looking at each one of these, what's the probability that you get two tails in the case of event 1? Well, that's going to be 0 because 2 tails is not in that event, times 3/4 plus the probability that TT occurs given event 2 occurs. Well, that's 1 because it absolutely occurred, times the probability 2 occurs, which is 1/4, which equals 1/4, which is what you expected. Okay, well, this was the problem is that a lot of times the law of total probability for simple cases seems like overkill because seems like you could get the answer and easier just directly. But the point is then that we can then apply it to cases where it isn't so simple. Let's now look at page 285. Problem 16, and see if we can figure that out. Okay, this is a little bit more involved problem. So let's at least try to understand it, and then we'll work on it. Suppose that we have 2 boxes. Each box holds 10 red balls numbered 1 through 10 and 10 blue balls numbered 1 through 10. We pick 1 ball from each box. Okay, so we have 2 boxes, and we have here 10, we have R1 up to R10 and B1 to B10, and over here R1 to R10 and B1 to B10. So they're identical boxes, and they have each has 10 red balls, each has 10 blue balls, and they're all numbered. Okay, so the experiment is the probability experiment is pick 1. Here's the left box and the right box. We pick 1 ball from each box. So, for example, a possible outcome would be red 4, blue 6. This would be from the left box and the right box. This is our notation for an event. Now, if you just to get familiar with this, what's the size of the sample space? Well, I can choose any of 20 possibilities here and choose any of 20 possibilities here. And what I pick from the left is independent of what I picked for the right. So the size of the sample space is going to equal 20 times 20, which equals 400. So the size of the sample space here is 400. Now, the problem is then, what's the probability that both are red given at least one of the two balls is red? Okay, so this is the probability that let me write this, 2 red given that at least one ball is red. Okay, we're going to have to we have to give a little code because we have to write this probability 2 red given 1 red. So it's a little bit less. Okay, well, it's a conditional probability, but then, and so we know from the definition, this is the probability that you have 2 red intersection 1 red. So you don't apply the law of total probability to this. It's going to be, we're going to apply it to these ones up here. This is the probability of 1 red. Okay, well, what's the probability that if 2 are red, given that 1 is red? Well, that one, if the event that 1 is red, if they have to both occur, well, the second one, this set here, the set with 2 red is a subset of the ones with at least 1 red. So this intersection is just going to be the probability with 2 red. So this is going to equal the probability of 2 red over the probability of at least 1 red. So the idea then is to use the law of total probability to figure out what these probabilities are, because you can. So that's the problem that you have to sort of figure out. Then is, given this problem, what would be a good partition of these? I mean, we could calculate just the straight numbers, and that's of course possible here, that we could do these two probabilities independently, but it might be that what we can do is we want to calculate each one of these using some partition of the left and right. So what I want you to think about is choose a partition that is good for this problem. Okay, we will now, well, hopefully you've taken a moment and chosen a partition. I'm going to choose a partition. The strategy for doing this is you don't have any numbers here. So my events are going to be sort of event 1 will be red, that both of them are red. Event 2 will be say red, blue, and event 3 will be blue, red, and event 4 will be blue, blue. What I mean is, so this one will occur, there'll be like any of the 10 red ones here times any of the 10 red ones here. So there will be 10 times 10, there'll be 100 elements here, 100 here, 100 here, and 100 here. So and they're mutually exclusive in the sense that if it's red, red, it can't be red, blue, or blue, red, or blue, blue. And this is useful. Let's see how it's useful or not useful. So let's try to figure out let's write out the law of total probability. Well, okay, what I want you to do is maybe you can write out um, the law of total probability for this one here, and then I'll pause and give you a second to do that. What's the law of total probability? Oh, and let's come up with, we have to make it easier. Let's say we have R2, it means you have 2 reds, okay? So I'm going to,
I'm sure I'll figure it out once you
okay,
explain it.
well then it's going to be plus the probability that you get 2 reds, given that you have that this event occurred, times the probability that that event occurred, plus the probability that you get 2 reds, given that this event occurred, times the probability that that event occurred, plus the probability you get 2 reds, given that this event occurred, times the probability that that event occurred. Well, the idea then is we can then write out these, well, what's the probability that you get 2 reds in this first event here? Well, these are all the cases of 2 reds. So that means that it's always going to occur. So the probability that if this event has occurred, because this is an outcome in this set. So the probability is always going to be 1. That's conditional probability times the probability that you're in this event. Well, that's going to be 1/4, because that's 100 over the sample space size of 400. This will be plus the probability that you get 2 reds, given that the left was a red and the blue was a right, is 0, times 1/4, because each of these is 1/4, plus 0 times 1/4, plus 0 times 1/4 for this last one. So the answer is going to be 1/4. Well, that's just in this context, that's the numerator up here. So the probability that you get 2 reds, that's our R2, given that you have 1 red, is going to equal 1/4, because we just calculated that, over the probability that you get 1 red. And you can also check back, does this make sense? This is the law of total probability, but if you look at these and you can see that, well, the number of ways you can get a red here and a red here is going to be, there's going to be 10 ways to get a red here and 10 ways to get a red here. So the number of RRs is going to be 100 and the total number is 400. So the probability is 1/4. So this is just not so hard. But then we want to use the probability that you get, let me maybe write it like this, that you get at least 1 red, because that's the denominator. Well, we want to divide it up with the same sets, okay? And see if you can write out the law of total probability. Write it out. You're writing out for this, but write out this formula and see if you can fill in the probabilities for the denominator. And I will zoom. Okay, well, let me just write down, this is going to be, it's going to be look just like this. The probability of 1 red, given that both are red, times the probability that both are red, plus the probability that 1 is red, given that the first is red, plus the probability that 1 is red, given that the second is red, plus the probability that one is red, given that both are blue, probability of blue. And so then, well, the probability that one is red if they're both red is 1 times 1/4 plus, well, if one is red, if one is, that's like 1 times 1/4 plus the probability that one is red, given that the first is blue and the second red, is going to be 1 times 1/4 plus the probability that one is red, given that both are blue, is 0 times 1/4. Okay, and then so that's going to equal 3/4. Well, so then the probability that two are red, given that one, at least one is red, is going to, at least one is red, is going to be 1/4 over 3/4, which is going to equal 1/4 over 3 times 1/4, which is going to equal 1/3. Well, I mean, that's a sort of surprising result in the sense that in these numbers here and in this sample space size, you don't see any threes. So that's one of these weird things with conditional probability. So if you know that at least one is red, essentially what that I mean, if you essentially what that's saying is the thing that I'm cutting out is that they're both blue. And there's sort of, that's like 1/4 of the cases. So again, you're ending up with the sort of, it's like a more complicated form of a conditional probability, but it's harder to see that because we've got this extra information about all these marbles in the left and the right. So this sort of illustrates how to use the law of total probability if you're given a conditional probability, is that you use the definition of conditional probability, then use the law of total probability for the numerator and denominator. Now, for these kind of problems, you could also figure out the numerator and denominator. Like you could go up and say, well, the probability that at least one is red. But essentially what you're doing when you do the counting is sort of dividing it up into these different events of red, 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 blue, blue, red, blue, blue. So in some sense, you're doing intuitively this law of total probability when you do the counting. So hopefully this makes sense for this situation. Now, so there's some other problems here, 17, 18, 19. We can continue with those on Thursday, but let me just comment that there's two puzzles at the end. This is the last topic in the chapter, and there's two puzzles. We did the birthday problem, and the second one now is the purple probability puzzle, in which you have two jars, and you have, let's see, how many marbles? You have 50, I think 50 red marbles and 50 purple, and you have a left and a right, and you're going to reach in and get what you're going to choose. You're going to sort of randomly choose left or right, and then choose which. If you choose left, you choose a marble from the left. From the right, you choose a marble from the right. So you can distribute these any ways you want. So presumably, so there's at least a, yeah, you can distribute them any way you want. So the idea here is to propose a distribution and then use the conditional probabilities, basically the law of total probability, to understand this. For example, one partition might be you chose the marble you chose is on the left, and the marble you chose is on the right. And so you could use those two events as a partition of the sample space, where this event is that you chose a marble on the left, this is event you chose a marble on the right. So the sample space is sort of the union of these two events, and you can use, and then the intersection is 0, is the empty set rather. So this is a partition of the sample space. And so the problem is you don't know what the you have to distribute the marbles so that, and so just distribute the marbles and figure out using a law of total probability what the probability of a purple the probability of a purple marble, of at least one. Well, you've chosen one marble. That what's the probability that you choose a purple marble given whatever distribution you have? And so you can, this is an absolute probability, but you can then write it as the law of total probability, and then figure out those probabilities given your distribution, and then understand how that will help you to understand how to distribute these in such a way to maximize your chances of getting a purple marble. Okay, it's 10:52. And the second problem, of course, is the Monty Hall problem, Monty Hall puzzle, in which you have the same two-step thing, but then you can also understand this via conditional probability, and the two situations of whether you switch your choice or don't switch your choice. And we'll continue with the examples of conditional probability, law of total probability, on Thursday. And this weekend we will have at least I think the further versions of concept check 2 and demonstration 2, and you can tell me on Piazza if you desperately need one of the other ones. Okay, so I'm going to